So I'm going to talk about ranking games and scheduling jobs. So let me see what time it is right now, so I have an idea. Okay, so basically I'm going to talk about three things. A little bit about rating systems in general. Then I'm going to talk about how I'm rating and how I'm tracking a game in the Quick Live. And then I'm going to talk a little bit about how I tune the ranking system to essentially make better ranking outcomes by automatic tuning by using CPU power. So 1 versus 1 games are the games I'm trying to rank. And 1 versus 1 games are games where you have 2 players that play against each other. And there's a winner, there's a loser, and in some cases there's a draw. But in this case, for Quake, there's no draws, at least not in duels. So there's always a winner. There's always a winner that you pick. So typical games of chess, Go, backgammon. You also have online games, which I mentioned StarCraft, not StarCraft, and Quake Live as examples. An emphasis is it's not a team game, so you always only have 2 players. If you want to rank team games, you need another algorithm than the one I use. So what is ranking? Well, ranking is that you basically go in and look at the history of the player. And by looking at the prior match results of the player, you obtain what is called a skill belief in how good that player is. So you put a number to a player, and the higher the number, the better the player. That's the basic idea. The problem is that you have a danger which is called the black swans in statistics. So perhaps the best way to explain it is by an example. You have a turkey and you have a man, and the man feeds the turkey each day, so the turkey builds up a belief and getting fed each day. Then the Thanksgiving event happens. And all of a sudden you have this event that happens that was not in the prior knowledge of the turkey. So now we have a problem. And the idea of these ranking systems are that they do not handle those. They basically hope that that's not what happens. So that's the basic idea of these ranking systems, that they believe that there are very few black swans in there. The metrics I'm using is which players are playing, for how long did they play. That's mostly because many games are in Quake are, for this thing, are 10 minutes. But you might end up in situations where the game goes on for less than a minute. And the reason is that one player quit early on because he is basically being destroyed. But really he made no effort in playing that match. Hence I read out all games that is less than 1 minute, because I'm guessing that the guy did not even make an effort in winning. I'm tracking a concept in Quake which is called the map. So you're playing on different kinds of levels of maps. And it turns out that map knowledge plays a big role, so I'm basically tracking what map did the duel happen on in the game. And then of course I'm looking at who won. And those are the only metrics I'm looking at when I'm building up my ranking statistic model of what is happening. So a player is given by his name and the map he played on. So basically, whenever you have a player playing on map 1, it's a different player than the same player playing on map 2. And this is in order to factor in the fact that map knowledge in this game happens to be pretty important. So in order to make it, to do that, I'm doing this. The problem here is that no sharing is happening, so I have no kind of complete knowledge of a player, how he performs over all maps. I'm basically regarding him as a new player whenever he plays a new map. And then I'm building up a statistical model on that. I'm trying to avoid having any more parameters in the system than who won, essentially. And the problem is that there's a lot of risk of adding more parameters into the model. So you could imagine tracking stuff like damage or how much a given guy in this game controls the items, which is very important, how many times he kills the other player, or other kind of parameters. And the problem of tracking those parameters and trying to factor them into the model is that you get a very complex model. And the problem with complex models are that they have a risk called overfitting, where essentially the model ends up being bad at actually predicting games. So adding too many parameters into the game is actually bad. So if I have two players, I have Alice and Bob here, and Alice has a ranking of 1600 and Bob has a ranking of 1750. And the question is, who is likely to win? Normally you would say, well, Bob has the higher score, so Bob is the likely player to win by some percentage. It's not important what percentage it is, but if I tell you that I'm very confident in Alice's rating by saying that the deviance of Alice's rating is 30, but Bob's is 250, then who is likely to win is perhaps not, oh, it's always going to be Bob. It might be, I'm believing much more in the 1600 score I gave to Alice than I'm believing in the other score I gave to Bob. So there's a point of how much confidence do I have in a given rating of a given player. And if I tell you this, that Alice has played 1,000 duels and Bob has only played 2, you might really believe in the skill rating of Alice, but the skill rating of Bob is basically just an educated guess at this point. So the way I rate is by a system known as Click2, which is created by Mark E. Glickman. The basic idea is that you have a system which is very much known from chess called the Elo rating system. The Elo rating system has one very big advantage. It's pocket calculator friendly. You can basically calculate it by hand if you want. But we have computers, so the idea is let us write a system that uses way more computer power in order to give better rankings for players. So rather than just Elo essentially just tracks a rating R for a given player, but I track two other values as well in my statistical model. I track a rating deviance or variance, which tells me how confident I am in a given R value, and I track a volatility, which basically measures how consistent the player is playing. And the reason I need this sigma, which is the volatility, is that otherwise I would have a player that has played like 3,000 matches, and he would have the confidence interval for that player would be very small. I would really believe I have that rating. But the system then would not, when he wins or loses, it would not move him that much in rating because it really believes this is the rating for the player. Now the problem is that the player actually improves. Then the player will consistently begin beating players that are above in rating. But it will take a long time for the system to move him up to the right rating he has. So by tracking this volatility value, I can figure out that this is the situation that happens. And I can then move him quicker to his right position. So this means the system will quicker get to find the right rating for a given player. So basically we have these rules. Players are given as an interval and not a single value. So players are starting with 1,500 in rating and a deviance value of 350. And we have a 95% confidence in the range of R plus minus 2 times the RD score. So that means that initial players, we do not know where they are, so we think they are between 800 and 2,200 points. And as they play more games, we basically find out, we basically look at who are they playing against, and that adjusts for his R and RD score. In general, the more games he plays, the lower the RD score becomes. But it does depend on who is playing against. And the sigma value is used as a tool to handle the problem where a player is improving so fast that it basically fools the rating system. So I can, in fewer matches, can figure out what is the real rating of a given player. So implementing Click2, it's on GitHub, so people can look it up. The primary problem, there's a paper on it, and it's very easy to implement. The primary problem is numerical stability of a root finding algorithm in there. So you have a function you need to find a root. And the problem is that the way you do it is, of course, you run a couple of million random rankings or quick checks. You just dump in 1 million runs or 8 million runs into the system, and you see what happens. And what happens is that the system goes into an infinite loop. You're going, why? So it turns out that it uses originally Newton-Raphson root finding algorithm, and that doesn't work. The problem is floating points, which are given by this f is a fractional part, so this is the thing between 0 and 1. Then you have a base and you have an exponent. So this is how you represent floating point values. The problem is that floating point values has hopes. So if I take this very large floating point value and add 1 to it and ask are x the same as x plus 1, I'll get true. Because adding 1 here, there's so large a gap between two values here in floating point values. So adding 1 is actually not going to give me the next value. I'm getting pushed down into the old value again. So this is a common problem with floating point. And it turns out what happens with the Newton-Raphson is that I have to have two values. I'm seeking a root inside it, and it's bouncing between these two possible values all the time. So it won't really converge. So I tried the Illinois method, which is another way of doing root finding. That didn't work either. It failed around 16 million test cases. And then Ritter's method actually seems to work. It survives the QC runs. So there's something there you have to be aware of with floating point values when you're trying to implement these kinds of things. Obtaining data, well, so the way you do it is, now you have a ranking system. You have a ranking system, now you need your 1.7 million matches, which there are. So how do you do that? Well, the data is public, but you need to scrape them. So you write a scraper, you back by a simple HTTP fetcher, some regex stuff, and some JSON decoding, and you have the data. You store the data in Postgres, because the data size per year is not very big, so just store everything in Postgres and be done with. A very important thing I use in all of my Postgres things is that I use idempotent a lot. The way you can see it in CS interpretation is that you say, well, stuff can happen at most once. So if I write something, it's either, it doesn't matter if I write it again, because I'm making sure that it's the same data I write. And I do a change at most once on the database. One of the tricks there is that I try to use idempotence in all of the data storage things, so I can avoid transactions. And originally the idea was that I wanted to try out React for this, but I don't need it, so I just stuck with Postgres. But I still have this idempotence thing where I'm essentially trying to look up things in a specific way. I'll tell you in a moment. So the thing I'm trying to do is I have a process that does something, looks up data, does some change, does some analysis, does something. And then the last thing it does before it stops is that it writes to the database, if all invariants are good. That means if the process crashes in between, it doesn't matter because it did not write to the database. So I'm trying to push the actually atomic write to as far in the tail of a process as possible. So it's always just before it stops. The system is built such that it has an always catch-up mode, in the sense that it is always trying to catch up to reality. It's always lagging behind by some epsilon time, and it's trying to catch up. So if the system crashes, actually the way data is stored, the data will be on the other end for about 2 months. So I have 2 months of possible downtime before I have to do something. Otherwise, I can just make the system catch up with whatever is behind. And the way I do it is that whenever I want to fetch some data, I just spawn a process that does it. And here you have the idempotence in play, because every 6 days I go in and look up what players needs to get, or a player needs to be refreshed every 6 days. So once every minute I look in the database and say, are there any players that need refreshing? If there are, I'm going to fetch everything about what matches that player played, store that in the database, and then do an update on the refresh value of the player. So here idempotence plays a role, because if I crash in between my update of the player, I'll still fetch the matches, and that means I'll still fetch some knowledge, but that doesn't matter because it will be the same knowledge as I fetched the last time. So basically I'm avoiding problems here by having a very specific order in which I write to the database. Matches are fetched one by one. As soon as I learn the matches from a given player, I can store it in a set and say these are the matches I need. And again, idempotence play a role, so when I get a match done, I can decode it correctly, I store it. And then, of course, the system is built such that I can spawn 3,000 processes per second if I wanted. The problem is, if I do that, then I crash the quick lifecycle. Because they cannot keep up. They can keep up with about, if people are sending more than a request per second to them, they get into trouble very often. At least they can see it on the graphs, so they tend to kill you if you do that. So the thing is, I could do it, but I won't. So how do you handle this? How do you limit your application now? You have this ability, you have this power, but it's essentially too powerful. So my basic idea is that I have a bucket of work I want to keep full. So I have a bucket of work, and I can just pour in up to 3,000 matches every minute into that bucket. Normally that would mean that the bucket would just increase in size infinitely. I'm registering every worker that needs to do some fetching. I register him with gproc, and I make sure that there's only one worker working at a given job at a given time. Now there is a race condition possibility there, but since the database is idempotent, I don't care. I just want to have the window as small as possible for probable idempotent problems. Then I built an application called Safety Valve, which does load scheduling of workers. So the idea is that you give it like this, a configuration that says, every 3 seconds I want to have some tokens added. I want to have 1 token added per 3-second interval. At max, I want 3 tokens in the bucket. And this maximum size of things waiting on the bucket is 90. And at most, 3 things must be running against the server and the other end. So this is kind of like a rule set for how I want to have my load balanced against the quick lifecycle. And the way it works now is that when I spawn my processes, I spawn them with this, where I say, well, you're going to run the QL fetch queue, safety valve, and in the dots here, I have my actual thing that does the fetching. And now what happens is that these processes will actually be blocked based on the scheme given here until actually they're allowed to run. So basically the idea is I have a queuing system where I define that you're only allowed to execute, even that though you have 3,000 processes running, what will happen is that, first of all, the size limiter here will kick in and say, well, for almost all of the 3,000, you're not allowed to run anyhow because the queue is full. So now I'm down to 90 processes, and they'll be dequeued at a rate of 1 every 3 seconds because I'm getting to dequeue 1 every 3 seconds. And furthermore, if I do dequeue 1 and he's running, I'm not allowed to have more than 3 ones running concurrently against the quick lifecycle. So by using safety valve, I can just spawn a lot of processes in the system, put them into this bucket, and then define the drip rate in the bottom of the bucket out of the system. And that essentially means that I now can limit by changing the configuration file here, I define how much concurrency and load I can push on the quick lifecycle. The neat part about it is that you do not have to care. You just write your code as if you just spawn a lot of stuff, and then you have these queues in the system that limits down and make sure that things work like you want it. So yeah, I plan to talk more about safety valve later this year because it's in itself it's quite an interesting application. Then there's the part about modern computing, because one of the idioms I try to use in the system is that when you write systems, then the problem is that you have no control of all of your system today because modern systems are distributed. In this case, I have no control over the quick lifecycle, but I still need it in order to do my work. So the problem is that I do not control that part of the code. And I do not know what the foreign system will do. And that means also that in modern programs, it's actually the case that you do not control all of your program anymore because you're calling all kinds of other systems, and these other systems do stuff and they break and so on. And the funny thing is that most of the foreign systems are obviously built by random monkeys typing on APL keyboards, and they're writing intercal. So you have a problem here. And one of the things is, for instance, that you want to handle errors right now in your code by having nice small parts of your code that says, if this error occurs, I want to do this. If that error occurs, I want to do that, and so on. But the problem is that, for instance, the quick lifesite sometimes returns an HTTP 502. But will it ever return a 504? We don't know. We could handle all of them, but no programmer is going to do that. So what you do, the solution here is that you use Erlang by saying, well, whenever something runs, I'm going to isolate the context, and if it fails for some reason, I'm going to crash that context along the way. So I'm going to use fault tolerance to handle this problem. So the errors I do know about, I can handle by gracefully just saying, okay, fine, you're probably a bit loaded, I better back off. And the things you do not know about are the ones that will crash your process. But at least it will generate a crash. And if you manage it, it'll only, you can actually handle the problem by handling it once and for all. So I have a little process inside the system, which is the finite state machines of two states. Either the system is operating as normal, or I think the quick lifesite is overloaded. So whenever I see something I do not know, I trigger this fuse essentially and say, oh, you might be overloaded. And all the fetches are limited on this overload process. So basically you time out the quake side or fetching from the quake side for either 5 or 15 minutes. And that means that if I have, it also does a couple of other things. It has a counter on how fast I actually execute fetches towards the other side. And if I'm actually increasing that counter too fast, it'll blow the fuse as well and stop my application. So I build in a safety fuse in my own system, so if I have a bug in the rest of my system, this thing is a second layer that triggers and makes sure that I do not overload the side. And then the other thing is that if there's something that crashes in the other end, the fuse will also trigger and make me back off for 15 minutes. The interesting part is it actually makes the QQ system here handle quick lifetime upgrades, because when they upgrade, they begin giving you 5 or something values. And the system just says, oh, but then I have to do nothing for 15 minutes. 15 minutes later, they have upgraded the system, and you just keep on running. So the basic result of doing all this is that the system has basically not been restarted since the 1st of May 2012. It's just running. And the only places where I upgrade it is if I really have new code I add to the system. Then of course I stop it and start it. But there's been no things where the system failed due to some foreign thing happening on it. So that's pretty neat that you have a system where you know that it's just going to work unless you actually mess up. So finally, tuning the engine. Gligo2 is a system where you have these parameters. You have the tau, you have the sigma, and you have the initial RD of a player. The point is, do you have the sigma and the RD I've talked about. The tau is a value that says how much it is worth to win a match, essentially. So in a game with a lot of randomness, it's not worth very much to win a match. In a game with very little randomness, it's worth considerably more to win a match. So for instance, if you take chess versus backgammon, backgammon has a random component because you're throwing dice. So essentially the tau value of that game would be lower than, say, chess, because in chess you do not have that kind of thing going on for you. The question is, how do you pick the optimal value? And the way I do it is that I say, given a year's worth of data, I use the first, I pick out the 3 last weeks, and I remove them from the set. Then I train the system on the first 49 weeks, and then I predict by saying how well does that parameter predict on the 3 last weeks. So basically now I can try different values of tau, sigma, and RD, and I can ask the system how well do you predict if I set it up like this. And then the goal is, of course, let me optimize for getting a better prediction here. So the way you do it is I use something called simulated annealing. People are familiar with that. Some are. So basically the idea is that you you're trying to build a system that wants to tune for some parameters. And you could say, let us run 1,000,000 runs where my parameters are chosen at random. And that gives, and then pick the best one. That's one way of doing it. But that wouldn't really work very well. The next thing you could say is, okay, fine, if I have a value somewhere, I could try in the neighborhood around that value. So I could mangle my other values a little bit and then go in a direction. And if that direction is better than, if that value is better than the one I already have, I pick it. Otherwise, I do not pick it. So that's called a hill climbing search. So basically, the idea is that you have a blind mountaineer standing somewhere on the mountain, and then he's tapping with his foot, and if he hits something where the slope goes upwards, he walks to that spot. If it goes downwards, he won't walk. So this blind mountaineer will, at some point, climb to the top. Right? That's the idea. The problem is that the top he reaches might not be the highest top. So he might find a local point, but not a global point where it's best. And since he's blind, he cannot see the other point. So simulated annealing tries to avoid that by placing the idea of a wire which is glowing that then fades out or anneals. So when the system starts out, the wire is glowing, which means that you are allowed to basically walk totally randomly with the total random pattern. And then as the wire cools down, you make it less and less likely that you walk randomly. You become more and more like a hill climber. So basically, you are slowly moving from a total random pattern to a hill climber pattern. And that means that hopefully the randomness will make it more likely that you will hit the top point, the global maximum, than you will hit one of the local ones. It takes a lot of computation, so 8 cores, 24 hours. I need to do it 1 and 2 times a year in order to optimize these values in the system. But it does improve the prediction rate by a couple of percent, so I think it's worth doing. I've done everything in Erlang. I could be faster if I did it in C, I think. But the problem is that the current bottleneck is ETS lookups. So I guess that if I were to do it in C and I get faster, where it would be worthwhile, I would need a completely different approach than the one I'm using right now. Because ETS lookups are really, really fast. So currently I'm kind of rooting for not worth it, so I just keep it in Erlang. And of course, as core count increases on the machines, it'll become less of a problem because I actually do parallelize my annealing algorithm overall, of course. So it improves ranking, but not by that much. So the results I have is that I generally do better at ranking than yellow, way better. And I do per-map rankings, which are way more accurate. And most importantly, I hit the right ranking of a player with only very few matches, like 10, 12 matches, and I know very precisely what the player is in the system. And finally, the neat part about building the system like this is that you can actually employ it on other games. It's not necessarily for Quick-Launch. You can take the Lego system and employ it on your own little App Store toy game you have made, and then you could just make the system auto-tune itself. I did not put out the annealing algorithm yet, but I'll do it. So you have that as well. So you can auto-tune the statistical model to your game with your parameters, which is kind of nice. So let me just show you what it looks like, just so you have an idea. See if I can find it. So let me take this one. So I'll zoom it because you cannot see it right now. But if you take one here, you have the players. Oh, let me go a bit out again. So you have players over here, their name, and then you have their confidence intervals here at how far they are. So let me go down to the bottom. So here you have the rating on the x-axis. So for the map toxicity, you had, for instance, this player here. He has a rating around here with this confidence interval. And then you can see that the American up here is better on this particular map, and so on and so forth. It predict this is taken from DreamHack Winter 2012, so it's pretty recent. And I think in this case it predicted 88% of all matches correct for all the players. So if you went in here and you used this as a betting engine, you would hit the right bet in the 80% of the time. So I also can show you there's also an interface here, of course, built with Cowboy. So you can just ask for players here and they get added. You have all the maps. You have their rank development, how the rank is increasing or decreasing over time. You have their ranking here with the confidence interval. I plotted as a box plot. You shouldn't, it's not a box plot. It's just for getting the confidence interval. And then you have the match streak, which shows you whether or not the last 150 matches, whether or not they were wins or losses. So if you sum all the match streaks, then you would get 150. And then of course you could just add more players like we had before. And you just add them to the thing. So people are using this a lot in Quake because they can go in here and they can see, hey, how well do I perform against this player and which map should I pick against him because it's really, really bad on that one. So it's an unfair advantage if you happen to know that you are not, which is a bit hidden at the moment. So, yeah. So I'll take questions from here on out.
So is this how you take unfair advantage of the other Quake players?
Yeah. Don't even go there, right?
What's your ranking?
My ranking, I'm miserable. I can add myself. So these are kind of like the best players in the world. These are kind of players I play against and lose against. This is me. If I can, I have to add that. So this is me on this map, right? So I'm a really good player. Apparently I spent way too much time ranking stuff, right?
You seem to have gotten weaker lately.
So answer the question, I'll start with that.
I understand the purpose of the variance, and it seems like a good idea, but it also seems like you can trick it. And it's lucky that people's rank development plateaus out, because otherwise it seems like you could have somebody who trended positively and continued to trend positively, so they had a wide variance.
Right.
But if you looked at their trending instead, you could make a better prediction instead of just saying, oh, they have a wide variance, because I didn't tell you that it went up. I didn't tell you that it went down. I just looked at it. There was a lot of change.
Yeah.
So if you looked at the trending, it seems like Echo 2 would be a little bit better.
Perhaps, I don't know. I don't know if it
You
would
were
be
asking
better.
about Mary versus Bob or whatever,
Uh-huh.
and if we saw that Mary was shooting straight up and Bob was diving down, maybe we lost a few.
Yeah, so one of the things I do in the system is that I'm ranking every week, and if you're not playing a week, I'm actually increasing the variance of every player by the player. So that incorporates the fact that if a player is not playing, I have less confidence in the current rating of the player. So if the player has not played for many weeks, the interval will grow. Now, if the player then plays, we'll move him, but since he has a larger variance, we'll move him faster. So if,
Data thing they're comparing themselves against, which is the Quake game.
Right.
It was like the stock market or something like that.
don't use it for bad idea. Bad idea. I don't think it would work. Yeah, Jack.
So let's cut to the chase here. This could work for tennis, right? So does it work with something like that where you don't have a lot of games though? Like you think Federer versus Nadal, like their total game history is maybe like.
I don't know. I have never tried it. The code is free. You can just download it and try it.
That's your game. But I mean, even if they can
Games are not independent.
That's a question.
You mentioned chess and Go.
Uh-huh.
If you try to do this with systems that have handicapping, like in Go, you justify being 2 ranks higher by saying
Right.
you give you 2 free
Yes.
moves, and they're
You have the
playing
same thing in chess because white has a movement advantage.
Okay.
White moves first. So actually, if you look at yellow and you go into the stats, then having the white pieces corresponds to a 35 yellow advantage.
So it's still almost
So there
just
is-
like a flat
Exactly.
increase
So
in
there
your
is
rank.
for certain things, if you have a given handicap or something, there'll be or if you have a given situation, there'll be an advantage of having that. And the same with a handicap. You can measure by tuning the system to the handicap. You will be able to measure how much a handicap is worth.
Oh, okay.
Because that's the problem. You do not know what the handicap is worth. So you have to essentially predict into the game what it is worth. You have to tune the system in order to understand how much does it need to have a handicap of something.
Right.
But the problem with that is, of course, is that whenever you add a new parameter that you tune for, you risk overfitting, which essentially is that you have so many parameters that the parameters uniquely identifies all the prior gains, or too uniquely identifies what you have. And that essentially means that your predictor becomes really, really bad. So you end up having perfect prediction, but you really did not tune the system for one, because there's too many parameters.
Right.
So what you end up doing is that you are going to say, okay, I have these 3 recent matches, and the first match can uniquely be identified by those parameters set like that, and the second one can uniquely be identified by those parameters set like that. Essentially, you are locking the system. That's the danger of just adding more parameters to the system. So you need to really be know what you're doing if you're trying to do that. There's a question about that.
The safety valve project.
Uh-huh.
I don't know if it does it already, but we have plans for adding like parameterized safety valves. If you want to scrape like a user's Facebook feed or whatever,
Right.
and that's the rate limit in the API, you can sort of parameterize it by the user and then keep the rate limit within whatever band that Facebook says you can follow.
So currently it cannot do it. If you wanted to do it, you would probably, the easiest way to do it is probably just to add a lot of views and then hash the users. That would be a very quick way to do it. But there's no built-in that makes it possible to do individual streams per something. Not right now, at least. It should be possible to add them. Safety valve has a manifest that tells me that I have to understand the quick check model before I write the code for it, though. So I might, if somebody says I want to do this, I might say, what is the quick check model of doing it? So in order to make sure that it actually works.
Sure.
Yeah. Any more questions? No? Come and grab me later for a beer if you want more.